Good morning, my dear students. So we move to reaction mechanisms. Hope you did those examples and you got the answers. Now we move to Simon-Smith reactions. Simon-Smith reaction is a particular reaction to prepare cyclopropane derivatives by using carbenes and substituted carbenes. So reactions of carbenes is very common. Usually carbene addition to double bonds give you many side products along with the original product. That means if we use free carbenes for addition reactions, it gives a large number of side products. That means the free carbenes could either undergo insertion reaction between oxygen hydrogen bond, or it could undergo insertion reaction between carbon carbon bonds, or it could undergo insertion reaction between oxygen hydrogen bonds. So Simon-Smith reaction is an alternative to this. That means in Simon-Smith reaction a cyclopropane derivative is prepared using carbene as the intermediate generated at the site of the reaction. So it involves the treatment of a double bond with diiodomethane CH2I2 and zinc copper couple to form cyclopropane derivatives. Or we could say the reaction gives cyclopropane derivatives without the formation of free carbene intermediates and without any insertion side products to double bonded compounds. So the reaction should be with double bonded compounds and diiodomethane in presence of zinc copper couple. See here, I have an alkene here. I am treating this particular alkene with zinc copper couple and methyl iodide. See, this particular methyl iodide contains a carbene CH2. Carbene is there, and we know carbenes are species having a lone pair of electron but no charge. So this carbene get introduced at the double bonded position to form cyclopropane derivative. This particular reaction is called Simon-Smith reaction. That means in Simon-Smith reaction there should be an alkene. There should be methyl iodide in presence of zinc copper couple to have a cyclic cyclopropane derivative molecule. Take down. See, the reaction proceeds through a carbene equivalent or a carbenoid. That means this carbenoid or carbene equivalent is a species that produce carbene without forming a carbene intermediate. That means in the medium there is no carbene intermediate is produced, but a carbenoid or a species which could easily transfer a carbene intermediate to the reagent is possible. So the reaction, in this reaction, the carbenoid is an organo-zinc intermediate. That is the attacking species, which is formed from methylene iodide and zinc copper couple. So methylene iodide and zinc copper couple react in the first step of the mechanism to form a carbene equivalent or carbenoid, and this carbenoid does not have a free carbene intermediate, but it provides carbene in the second step of the reaction. See here, I have methylene iodide or diiodomethane CH2I2 and have a zinc copper couple. This zinc metal have an innate power to enter into the bond between carbon and iodine, that is the insertion reaction, to form Simon-Smith reagent. So ICH2ZNI. Zn is getting inserted between carbon iodine bond to generate the carbenoid, which is called as Simon-Smith reagent. Take down. So in the second step, these carbenoids will transfer the carbene from the metal to the alkene without a free carbene in the medium. So the carbenoid formed in the first step transfer the CH2 group to the double bond without leaving the carbene as such in the medium. That means both new CC bond, a cyclopropane derivative is forming. That means the CH2 has to connect between two carbon atoms. So both CC bonds are formed simultaneously, and the nucleophilic CC causing loss of iodide leaving group and the electron from the nucleophilic carbon zinc bond being used to form the other carbon-carbon bond. Check here. See here. This is the carbenoid intermediate. Simultaneously, this bond is attacking to this particular carbon atom, and soon the electrons are attacking to this carbon atom. So iodine is leaving here, and the metal zinc is donating the bond pair of electron between carbon and zinc to this carbon atom. That is why the leaving group, that is the iodide group, and the lone pair of electrons or the bond pair of electrons from the zinc is attaching simultaneously. So Zni is leaving as well as iodine is leaving to form Zni2. So simultaneously the CC bond is forming in the Simon-Smith reaction. So see here, this bond is attacking to this carbon atom, iodine is leaving here. Simultaneously, zinc is giving the bond pair of electron between zinc and carbon to the another carbon atom of the double bond. See here, simultaneously the carbon-carbon bond is forming, leaving Zni and I as Zni2 to form the cyclopropane derivative. Take down. Cyclopropane formation usually takes place in the less hindered phase. So when we are taking bulk molecules and there is steric hindrance, so the cyclopropane occur from the less hindered side, and the reaction is stereospecific with respect to the alkene. That is, if the alkyl group of the alkene is cis, then they are also cis. See here, cis-2-butene. I am treating with CH, that carbenoid, that is Simon-Smith reagent, so that I will get the cis derivative. And if I use trans-2-butene, I will end up with the trans derivative of cyclopropane. So this is highly stereo-specific reaction, Simon-Smith reaction. But if we use direct carbene to this reaction, it is never stereo-specific. So simultaneous attachment of carbon-carbon bond is making this reaction is stereo-specific one. Take down. Now I have given you 3 reactions. Take down the reactions and write the product now itself. Okay, I will just give you 1 minute. Write down the reactions and confirm the products. Okay. Okay, check the answers. See, here is the double bond. The double bond, it is acting. Here it is double bond here. So it is acting here. And in this particular molecule, we have double bond here. So the cyclopropene is coming there. So for examination, I am giving you compounds with 2 double bonds. Let me see how you are going to answer. Now we move to another reaction, that is Willsmeyer-Hack reaction. Willsmeyer-Hack reaction is a common reaction used to formylate aromatic rings. Formylation means to add CHO group to the aromatic rings or aromatic rings which are active. For this formylation purpose, the reagent used in Willsmeyer-Hack reaction is phosphorus oxychloride and substituted or disubstituted formamides. So dimethyl formamides or disubstituted formamides with POCl3 act as the reagent for Willsmeyer-Hack reaction. So the reaction is used to convert electron-rich aromatic compounds to an aryl aldehyde. So the condition is that the ring should be electron-rich and there should be disubstituted formamides and phosphorus oxychlorides or POCl3. And this reaction is given as here. See here, I have a aromatic ring where I have the groups which are OH group or OAR group or NH2 groups. And I am treating with the dimethyl formamide in presence of an acid chloride, that is POCl3, so that this reaction undergoes to form a formylation here, that is CHO. A CHO group is introduced here. So we are getting a aryl aldehyde. This reaction is called Willsmeyer-Hack reaction. Take down clearly and carefully. So the first step of the mechanism, an iminium ion is formed by the reaction between disubstituted formamide with phosphorus oxychloride. Willsmeyer used dimethyl formamide with phosphorus oxychloride and he got the intermediate and he named it as the Willsmeyer reagent. Now we could use any disubstituted formamide. It reacts with phosphorus oxychloride in the first step to develop, to produce an intermediate, an iminium ion. This iminium ion formation is the first step of the mechanism. See here, this is phosphorus oxychloride. Now this is the substituted formamide. So the lone pair of this nitrogen get into the bond between nitrogen carbon. This is nitrogen carbon bond. As a result, this electron, this is C double bond O. As a result, this bond shift to the oxygen here. O minus will come here. And O minus will attack the phosphorus atom. And Cl minus will be released. You write along with me, please. Draw this one, substituted formamide. Show the lone pair of electron over nitrogen. Then show the arrow mark. It is shifting between nitrogen and carbon. As a result, carbon double bond gets CO minus. This is O minus. That minus will attacking the phosphorus. And when this O minus attack the phosphorus, Cl minus will be eliminated. And I will get Me, N, Me. The nitrogen has lost a lone pair of electrons, so it is a positive charge over nitrogen. Nitrogen carbon double bond. There is a hydrogen already here and oxygen linked to phosphorus. Now the released Cl minus will come and attack this carbon atom. The released Cl minus ion, draw it, the released Cl minus ion come and attack the carbon atom having carbon nitrogen double bond, carbon nitrogen double bond. As a result, this bond will be cleaved. That means phosphorus always have a tendency to have P double bond O bonds. They have a driving force to P double bond O. So this will be shifting towards here. That means PO2Cl2 will be eliminated out. So I will get Me, N, Me, Me, N, Me. Positive charge is there. And C, HCl. So this is an iminium ion. So this lone pair of electron could be shifted back here and this carbon can have the positive charge. So we are getting, or we could say this positive charge will be neutralized by the Cl minus ion to have a salt like structure. So in the first step we are getting an iminium ion which is the intermediate of the first step reaction, and along with we will be having PO2Cl2. Now we are moving to the second step. So draw along with me. Draw the benzene ring. Draw the benzene ring. And this benzene ring is having lone pair of electrons, delocalized electrons. So this bond is shifting towards this carbon atom. As a result, this carbon atom, the first carbon atom getting a negative charge and the second carbon atom is getting a positive charge. The negative charge present on the first carbon atom attack the carbon atom of the iminium ion. When it get attack the iminium carbon atom, the lone pair of electron or the double bond between nitrogen and carbon shift back. As a result, I will get a structure like this one. See here, carbon, iminium carbon bond has established. That is, the carbon atom of the benzene ring or the aromatic ring is forming a bond with the carbon atom of the iminium ion. And chlorine of the iminium ion already there, hydrogen of the iminium ion already there, this hydrogen atom of the benzene is already there, then Me2N, dimethyl substituted amide. Now this H plus, this carbon H will shift towards here, When it shifts towards here, the positive charge will disappear. See here, the H plus is eliminated. As a result, I will get a structure like this. A delocalized benzene ring to which carbon-carbon bond is established of the iminium ion. Then chlorine is there, H is there, Me2 is there. Now the lone pair of electron present in the nitrogen of this disubstituted formamide, that is the lone pair electron present in nitrogen, gets shifted here. When it gets shifted to the carbon nitrogen bond, naturally this Cl minus will be eliminated out. So the Cl minus will be eliminated out from the molecule. How? When the lone pair of electron present in the nitrogen is getting shifted between carbon nitrogen bond, the Cl minus will be eliminated out. At this juncture or at this junction or at this spot, water molecule come and attack. See, this is water molecule HOH. So the oxygen atom of the water molecule get attack the carbon atom. As a result, this bond will be shifting back to the nitrogen. So H plus will be eliminated out. This eliminated H plus will come and attack the lone pair of electron of nitrogen. So NH bond is established again. Check clearly. See here. This is HOH bond. This bond will be attacking the carbon atom. As a result, H plus will be eliminated out. When this O minus attack here, naturally this carbon nitrogen bond will shift towards the nitrogen atom. So the nitrogen atom will lose the positive charge and that nitrogen atom will abstract the H plus ion of the water molecule, resulting the formation of benzene ring, carbon, OH has come here, H is already there. Now Me2NH is formed with nitrogen having a positive charge. Now this oxygen hydrogen bond is shifted towards the benzene ring or shifted towards the carbon oxygen bond. As a result, this nitrogen carbon bond undergoes shifting. So we will get the corresponding aryl aldehyde with the dimethyl formamide. This is the second step of Wills-Meyer-Hack reaction. So we could summarize: the aromatic ring or the arene attack the iminium ion, followed by hydrolysis gives the final product aldehyde. During this process, H plus will be eliminated, Cl minus will be eliminated, and finally Me2NH will be eliminated out to form the aryl aldehyde. You got it? I hope you got it. Take down carefully. Check your book and my PowerPoint. So Wills-Meyer-Hack reaction is applicable to aromatic hydrocarbons, amines, phenols, and even to heterocyclic compounds if the ring is active. Though N-phenyl N-methyl formamide is a common reagent used, other aralkyl amides and dialkyl amides also could be used. See here, this is a heterocyclic compound. And this heterocyclic compound, I am showing the intermediate here. Attack the intermediate, that is the iminium, chloroiminium ion. Followed by the reaction, I am getting a CHO group introduced into the heterocyclic molecule. So this is an easy reaction where I could easily bring in synthetic reactions. I am taking small molecules and making to bigger molecules by different steps of reactions. So Wills-Meyer-Hack reaction is a simple reaction that could be easily used to introduce a CHO group to the heterocyclic rings or aromatic phenols or amines or aromatic active hydrocarbons. So it could be easily using phosphorus oxychloride and dimethyl formamide. We could easily introduce a CHO group to the heterocyclic compound. Take down importance. Now take down this reaction. I have a compound here, an active aromatic ring, and I am treating with dimethyl formamide and POCl2, sorry, POCl3, followed by hydrolysis. Write down the product. I have second one, that is a pyrrole pyridine derivative, treating with dimethyl formamide and POCl3. Complete the reaction. Sojia, write the reaction. Don't look or take screenshot. Check the product. See, I am getting two products here. See, I have CHO here. When these two get introduced, I have a 60% chance for the third one. So CHO is getting introduced, formulated to two rings, and finally I will get, if the reaction is continued for a long time, I may get three rings undergoing formulation reaction. See here, I will get CHO group here. Here near to the nitrogen atom is very active. That is why I am getting CHO introduced here, or I could get here. So take down these reactions, complete the product, and do it as a homework. See, I have a OMe derivative here. It is an active aromatic ring is here. See, an aromatic ring, active aromatic ring due to OMe. Here I have another heterocyclic compound here. Just check here where the substitution occurs. And here I have an active aromatic compound and I am using a substituted formamide. See, here a phenyl substituted, here a methyl substituted. This is a substituted formamide, not dimethyl formamide. It is phenyl methyl substituted formamide. So take down the reaction and write down the product. Let me see.